Hi, this video is a tutorial on what procedures to follow before running any tests on the squeeze film dampener test rig here at Texas A&M University. We're going to go through all the procedures again on what you should do before you can use the LabVIEW program to actually run tests again. The first step in this case would be take off the shield guard and the inlet hose. To do that, you pull on the tip of the hose right here, the connector, to release the valve, and then you can open it up and release the hose. Then the next thing would be to take off the cover or the splash guard of the bearing cartridge. Simply do that by redoing the screw, and then you can just set aside the splash guard into the containment center over here, since more than likely it would already have oil on the inner side of it. This is what I mean. There's oil already here, so just place it right here for convenience, and it'll keep everything neat and clean. The next step would be to remove this little connector right here that connects the hose to the journal where oil is supplied from. Alright, depending on how tight this little connector is here, you can use an adjustable wrench or screw it off by hand. In this case, we'll assume that it's too tight to screw off by hand, so we'll use a wrench. Once you loosen it up, then you can use your hand. Alright, the journal is attached to the bearing cartridge or the test rig through a hexagonal or hex screw down here at the bottom of the journal. That's actually the thing that holds the journal statically in place right here. To take that off, you need two instruments. One would be this hexagonal bar, and then you would need just the Allen wrench right here. The tools are usually set aside via the test rig that you need, the right sizes. And the way you would do this, since you're unscrewing it, you don't really need a torque wrench. All you need is to unloosen the bolt. You just put it in and just unscrew. Then from here you can just use your hands to unscrew the bolt until you know it's loose. Once the bolt has been completely unscrewed, you can take it out by putting a little bit of a momentum or torque on the bolt and slide it out of the journal. It's going to be covered in oil, so you can also put that one right here. Alright, now that the journal is unscrewed, it is not held firmly in place. But if you're ever changing out journals, you'll need a T-bar to screw it and pull the journal out of the bearing cartridge. You can find the T-bar sitting right underneath this power supply right here. Well, these are the two handles, and you screw this end into the journal. You'll see that the journal is already threaded, so you can easily just screw this in, actually, such as this, and then pull out the journal if you're ever replacing the journal with something else. Alright, this journal right here is the short length squeeze film dampener. We call it dampener E. There are 3 feed holes in the dampener, all spaced out 120 degrees apart. Each feed hole is designated by a dot, 2 dots, or 3 dots on the top of the journal. Note that this is important when you're aligning the journal into the bearing cartridge. Dot 1 is conventionally aligned with the static loader, or 45 degrees away from the X and Y coordinates. So now when you're placing the journal back into the bearing cartridge, you need to keep in mind that this needs to be facing the static loader. Keeping an eye on the dot right here for the feed hole 1, you place it back into the bearing cartridge. Don't worry if you don't get it aligned right when you put it in. The journal is still not held firmly in place by the bolt, so you can still turn it when it's sitting in the bearing cartridge unbolted. Once you're done with the T-bone, put it back wherever you found it, and now you can focus on aligning the journal in the right orientation. So, once again, here's orifice 1, or feed hole 1, designated by just 1 dot. To recall what we mentioned earlier, there's 2 dots on the feed hole 2 and 3 dots in a triangular pattern for feed hole 3. Remember that feed hole 1 is aligned 45 degrees apart from the X and Y coordinates or with the static loader. Now we're on the step to center the journal. To do this, we need spacers. There's one tool we use which gives us a variable spacing, which has the actual thickness of the film written on it. In this case, we're using dampener E, which has a clearance of 4.8 mil. So the closest spacer that we have to 4.8 mil is 4 mil. We will use this to center the journal. And the way we do that is by putting it between the clearance and seeing where the journal is tight and where the journal is loose. Here we can tell it's tight since the spacer is struggling to get in. Oh, on the other end, it's really loose, and it's quite easy to get the spacer in between the journal and the bearing cartridge. So we realize, or we know now, that this side is tighter than this side. So what we would do to center the journal perfectly, we can put in these thin sheets of aluminum that are cut to exactly 4 mil of thickness. Here we're going to use a thin one already cut for use in this video and place it roughly around the area that we think is the tightest. You can pull the journal actually a little bit to open up the space between the bearing cartridge and the journal to expand the clearance and slide in this spacer. So once it's in and we're satisfied with the spacing, you can visually check around the journal to see if all the clearance is about the same. Then you want to make sure, again, using the measured designated spacer right here, and see how difficult it is to slide in certain parts of the journal. As we test now in the same location that was previously tight, you can see that the spacer is helping out move the journal away from the bearing cartridge where it was tight before. Then we check on the opposite side and we realize it's still fairly the same amount of ease to slide it in. So we know that that side is centered pretty well. Put this right here. Takes a couple of tries, but don't be discouraged if you don't get it on your first one. I usually like spacing it out every 30 degrees and seeing how difficult it is to slide the spacer in between the journal and the bearing cartridge. If it slides in with just a little bit of friction, then you know it's alright. Sometimes it'll give you a problem, like if you try to put the spacer exactly where the feed hole is, it won't go all the way through. Since this feed hole has just a little bit of a protrusion that blocks the spacer. And there's also sensors built in around the bearing cartridge that have the same type of protrusion into the clearance or the film end of the journal. Now we can see that the spacer is going in every direction with pretty easily, so we're going to assume that it's centered now. Remember that the journal is not perfectly circular, so there are going to be certain parts that are always going to be tighter than the others. That's when the static loader comes in, and we'll go over that later in the video. After we've made sure the journal is centered, we need to retighten it using the hex bolt we took out earlier, sitting right here, and the two tools we used to unscrew it before. We put the hex bolt back in. Note that it should go all the way into the bottom of the screw. So there it goes. Make sure that it's in as far as it'll go. You don't want to leave any space because that will result in grinding of the threading of the bolt. Put it in and just screw it in manually until it becomes too tight to do that. Now that the screw is firmly in place, we need to make sure that we apply the same torque that we applied to the previous test to every other test following. In our test rig, we use 25 foot-pounds of torque, and we apply that torque using a torque wrench that sits right here next to the power supply. Be careful with the torque wrench, since it's a pretty expensive tool. The way you adjust a torque wrench is through these markings right here. Right now it's not set to exactly 25 foot-pounds. Right now it's actually set to 20 foot-pounds. So the way you adjust that is you pull back on this little handle right here and you turn it until it reaches the 25 foot-pounds mark. When the line of the handle and the bar meet, then you know it's set to 25 foot-pounds. Then you can release the handle and it'll be set to 25 foot-pounds. The next step is to take the Allen wrench and apply it onto the torque wrench so that we can screw in the bolt at exactly 25 foot-pounds. The way this works is you continue tightening the bolt, and when you feel that it's getting harder to turn, the torque wrench will make sure that you don't apply more than 25 foot-pounds of torque by bending once it's reached 25 foot-pounds. It clicks right here. That lets you know that's 25 foot-pounds have been reached and no more can be exceeded. If you pull any more than that, you might actually damage the torque wrench, which no one really wants to do. So now the generator is centered and held firmly in place by the bolt. Now that the journal is centered, replace the splash guard and attach the hose back onto the journal. So to do that, you just put this little cap back on the journal, screw it in, and then once you get it in, you can tighten it just a little bit with the adjustable wrench. Be careful not to put too much force, since the plastic will wear away through that. And then you can put the splash guard back on just the same way we took it off. Just a little screwing in. Just put that in there. The purpose of the splash guard, when you're running tests, there's going to be a lot of oil being pumped into the journal, and the feed holes are going to push against the filament, which actually helps increase dampening of the squeeze foam dampener. As the oil is shooting out the top and bottom ends of the dampener, we just don't want it to get everywhere on our test rig, so this thing just prevents the splash from going everywhere, and thus the name splash guard. So you put the hose back in by pulling on the top, letting it go, clicks in place, and it's in there solid. Now the next step after you've centered the journal is to signal condition and turn on all the power supplies. And the way you do that is by going behind this little tower right here. So, come back here and look at it. So there's three surge protectors right here that you turn on. The first one, I believe, goes to the power supplies for the pressure sensors, the load, and displacement sensors, and acceleration also. Then all the power supply for the revamp sensors is the second surge protector, and then finally for all displays such as the static loader and temperature displays up there, you turn on the last one. The last one also goes to the oscilloscopes that you can observe during tests to let you know that everything's working fine. Now we are going to go through the signal conditioning process. In this process, we want to set the voltage that's getting sent to the computer to 0, so we don't go over the saturation limit of 10 and negative 10 volts. And the way we do that is by first using these two multimeters. Turn them on, and you'll notice that each wire connected to these multimeters is labeled. So this is X and Y. And what that means, this is the voltage coming out of the X displacement center and the Y displacement center. And, these are the ones we want to signal condition to 0 volts. The way we do this is a multi-step process. So first we go through the X direction. So what you do is you take out the Y direction cable from this multimeter, and you go up to this cable right here. So this is the voltage that's actually going to be sent to the DAC board, which is what the computer actually reads. You want to replace the X direction revamp sensor right here from the oscilloscope readout and put it in here. So you'll notice that these two voltages are quite different. Here it's 0.5 volts, and down here it's 6.8 volts. Where saturation right now is turned on by the signal conditioner. That's what's causing the difference between the voltages. Right down here is where you'll find the signal conditioner. This section of the signal conditioner controls the voltage from the X direction displacement sensor. As I mentioned before, the saturation right now by the signal conditioner is on, which is causing the difference between the two voltages displayed by the two multimeters. Now when we turn off the signal conditioner, and make sure that off is right in the middle position. So right there, when we turn off the signal conditioner, in theory the voltage should be exactly the same displayed by the two multimeters. And then you can notice they become way closer to each other. The first step in signal conditioning is to match up the two voltages when the signal conditioner is off. So what we do is you flip this little switch over here to let the adjustable resistor be adjusted, and you turn the knob and you try to get the two voltages as close as you can to each other. If it's within like 0.05 volts, then that's okay. Now we've got the two voltages pretty close to each other, or as close as we can when the signal conditioner is off. The next step is to turn on the saturation and try to get the voltage reading out of this multimeter, which is sending voltage straight to the DAC board, to as close to 0 as we possibly can. The way we do that is by using this little screw and a little adjustable resistor on the signal conditioner. So down here, you'd mess with this thing and you try to get the voltage reading out of that multimeter connected to the oscilloscope as close to 0 as you can. So you just adjust it, and if I'm correct, when you rotate it clockwise, the voltage becomes more positive, and when you rotate it counterclockwise, it becomes more negative. You want to get to 0 as close as you can. Now the X direction displacement sensor has been conditioned to about 0 volts. The next step is go to the Y direction. You can do the same process, but all you have to do is replace the X rebar sensor back into this connection over here. That's going to send the conditioned signal from the X sensor to the DAC board now, but we still have to do the Y, so you replace the Y direction. This one's not labeled, but this is the Y direction. Let me just turn it here. Get this out, put this back in this multimeter, put it in, hold it right there, and you'll notice it's not 0, as well as the prior one. Try to get this here. Right, and now you replace the X sensor cable with the Y sensor cable on this multimeter that shows us the raw voltage coming off the sensor. Again, this is the voltage that's coming straight out of the sensor without being conditioned or anything. And you'll notice, again, they're not the same. So what you have to do is go down to the signal conditioner, turn it off, make them equal, turn it back on, and get this one to as close to 0 as you can. Just like we did to the X direction. So I'll go through that real quickly without talking. Right here. Turn it to off. Get close to each other as you can. That's pretty good. And we turn the signal conditioner back on. Use this little screwdriver to get to 0 as close as you can. Note that it's really hard to get to 0. So about 5 millivolts is pretty good. Both directions have been signal conditioned. So we need to get the last bit of procedure set for the test to begin. What you do is you take out this cable, put it back in the oscilloscope, which is going to send the conditioned signal from the Y sensor to the DAC board, so the lab view program can read it and record the results. Replace the X and Y cables right here into these multimeters to show the raw voltage, which will be helpful when you're trying to set up the eccentricity of the journal. The next thing is to turn on the pump and the suction thing of the journal so we can get all the the bubbles air out of the oil we're going to use to lubricate our dampener. Turn it on here, go over here, turn on the oil pump, this switch right here. Ready? And then the controller for the oil pump is sitting right next to the test screen. This thing tells us, this thing controls the flow rate of our oil. So it's very sensitive, where you can adjust it using this little knob right here. Press run. Not that much. There we go. Turn it on a little bit. The pressure builds up as you increase the flow rate. Now what you want to do before you run any test, that's the flow rate. Before you want to run any test, you want to let all the oxidation in the oil work its way out. So you let it run for a little bit until all the bubbles go away. In the meantime, you can set the pressure that you want for test. We usually run at 27 psi, I think, gauge pressure. Around what we do. And we let it run and do its thing. And again, I may have gone through it pretty fast, but there's the switch for the pump to suction out the oil being fed in, and this is the controller for the feed flow, or the supply oil. Once you've got the oil running, you want to let it sit for a little while, or sorry, not sit, but let it run for a little while, so that the oxidation in the oil can work its way out. One thing you should note is that when we were centering the journal, if you can recall, it was tighter near the static loader than it was on the opposite side. So in order to get a perfect center condition or zero eccentricity, we need to apply a static load so that the bearing cartridge can move a little bit so the clearance all around the journal is equal. To do that, we usually use 40 pounds of load, pounds force, and the 45-pound direction using the static loader. You can play with this thing until you get about 40 pounds sitting up there. And you can notice, if you come over here, that the little spouts of oil coming out of each of the feed holes is about the same height, which means that the centering around each feed hole is about equal. The next thing to do is finally run a test. Now let's go over the setup once again before we run a test, just so you know what's going on. Here are the electromagnetic shakers that apply a force sent through a stinger attached to the bearing cartridge onto the bearing cartridge that causes displacement about the journal, which we measure and figure out course coefficients with respect to that journal. So before you can run a test, you want to turn on the blowers that send air to the electromagnetic shakers to keep them cool. They're very expensive, and we don't want the electromagnetic shakers to blow out. So we turn both of these on. You can see the labels on them. It's the X shaker or Y shaker. Turn them both on. And that sends air to the electromagnetic shakers. The next thing to do, we've already set up a LabVIEW document. If you read the test procedures document, you'll understand what to go through the LabVIEW program in order to run a test. But here we've already set one up, and we're just going to run it to show you what it looks like when you begin a LabVIEW document. Now we've set it up, and in order to run a LabVIEW, we just press run. You can look at the bearing cartridge when we begin the program. It's going to cause a deflection that you can see. So you can point the camera at the. Once you've got the test running, you can monitor the test by looking at these oscilloscopes. And then if you're running a circular orbit test, obviously you want a circular orbit. Over here, you can also look at the sensors in the LabVIEW program and just monitor the test to make sure everything's appropriate. And then the LabVIEW will do a lot of itself. You'll understand more about the LabVIEW document in the test procedures document already written. So that's pretty much how you run tests using the SFD test rig testing.